Hello everyone, welcome back to this online class. Today we are going to look at Lagrange interpolation technique. We have this question. We are asked to derive the Lagrange interpolating polynomial of degree 1 and hence deduce the interpolating polynomial of degree n. Once we have the polynomial, we now need to determine the collocation polynomial appropriate to approximate the following data. We have the table of x and f of x. Hence use your polynomial to estimate f of 2.5. So let's take note. We write NB that the spacing between the x values, what we are calling tabular points, need not be uniform. So unlike the case of Newton's forward difference interpolating polynomial and Newton's backward difference interpolating polynomial, where we require that the spacing must be uniform, in Lagrange interpolating polynomial, the spacing need not be uniform. So now, I need also to take note that such type of data where the spacing is not uniform, spacing between the x values, is not uniform, often occur as a result of experimental observations or when historical data are examined. So let's start with a polynomial of degree 1. So polynomial of degree 1, a simple interpolating polynomial of degree 1, polynomial of degree 1. So it is a polynomial of the form P1 of x is equals to ax plus b, where a and b are constants to be determined. So this polynomial passes through the points. Let me bracket this and say that it must pass through the points. It must pass through the points. Our point is x naught, f naught. Remember, f naught is the same as f of x naught. And another point is x1, f1. If I were to draw the table, it is this one, x values and f of x values. So that here we have x naught, f naught, x1, f1. Remember, it must be of degree 1, so we only need 2 points to be able to come up with such kind of a polynomial. So that kind of a table. So now with this table, we can be able to find the values of a and b. Now, let's start with the first point, x naught and f naught. So you can write here that let's call this equation star our polynomial. So you can just write put x is equals to x naught and p1 of x naught be equal to f naught to get. So we are going to get f naught is equals to ax naught plus b. This is the first equation. Also put x is equals to x naught, not x naught, but now in this case it is x1. And p1 of x1 is equals to f1 to get. That will now give us f1 is equals to ax1 plus b. This is equation 2. Remember, these equations can be written in matrix form, matrix vector form. So let me show you how to write them in matrix vector form. So this can as well be written as, we can start with F0, F1 is equals to X0, 1, X1, 1. Then here we have AB. We need to find the values of A and B. So this matrix can be written as A, the coefficient matrix. This you can write as the unknown column vector, not unknown column vector, but the right-hand side, that is B. This is B. And this one is the unknown column vector. In general, it is A times X is equals to B. Matrix vector form. A times X is equals to B. And so to solve this system, you can use Cramer's rule. It is easy to use Cramer's rule. So you can write this. Use Cramer's rule to use Cramer's rule. Let me show you how to get A and B. So A will be equal to the determinant. I replace the first column by the right-hand side vector. So that would be F0, F1. Then here we have 1, 1 over determinant of X0, X1, 1, 1. And so this determinant will be, in the numerator, it will be F0 minus F1. Denominator will have X0 minus X1, which you can just leave it like that. Then, how do we get B? B is the same as determinant. Now we are going to replace the second column of the coefficient matrix by the right-hand side vector. So we'll have X0, X1, F0, F1 over determinant of X0, X1, 1, 1. So this is the same as X0, F1 minus X1, F0 over X0 minus X1. So let's now substitute the values of A and B into our interpolating polynomial, that is equation star. Let's replace them here in this equation so that you see what you're going to get. So you can say it therefore P1 of X is equals to, our A is F0 minus F1 over X0 minus X1 times X, the whole of this times X, plus B, which is X0 F1 minus X1 F0 over X0 minus X1. Let us simplify. The denominator is the same. So that would be under the common denominator X0 minus X1. So what will be our numerator? We will have XF0 minus XF1, then plus X0 F1 minus X1 F0 over the common denominator, that is X0 minus X1. I want to factor out the coefficients of F0 and F1 in the numerator. So this you can as well write as X minus X1, that's the coefficient of F0. Then those of F1 will have plus X0 minus X This is the coefficient of f1 over the same common denominator, which is x0 minus x1. So this is x0 minus x1. So this can as well be written as, if I split them so that I have two fractions, you can as well write this as x minus x1 over x0 minus x1 f0 plus x0 minus x over x0 minus x1 f1. And you see the second term, I can be able to factor out the negative from here so that this can as well be rewritten as, I want to start with x minus x0, so you factor out the negative in the numerator and also in the denominator. So this can as well be written as x minus x1 over x0 minus x1 times f0. So it will be plus x minus x0 over x1 minus x0 times f1. So if I let this one to be a certain function of x, which I'm going to call L0, a function of x, and this other one is L1, a function of x. So then what will I get? I am going to get my polynomial to be, so you can just say hence, our P1 of x, can as well be written as L0 x f0 plus L1 of x f1. Of course, you can see our L0 of x and our L1 of x, the way we have defined them. So let me bracket this using another color. So this is a Lagrange interpolating polynomial of degree 1. So you can just say where what we are calling L0 of x is the same as x minus x1 over x0 minus x1 f0, and L1, a function of x, is equals to x minus x0 over x1 minus x0. So those ones are called Lagrange coefficients, or Lagrange fundamental polynomials, or basis functions. So you can just say are the Lagrange coefficients. Lagrange coefficients. So remember, for us to get that polynomial, in our table we had just 2 points. When you have 2 points, you get a polynomial of degree 1. So when you want a polynomial of degree n, you'll need to have n plus 1 points. So let me comment on this and say this is the Lagrange interpolating polynomial of degree 1. Lagrange interpolating polynomial of degree 1. So now we want to generalize this concept to a polynomial of degree n. So we'll need to get to have n plus 1 distinct points, or simply tabular points, so that we come up with that polynomial. So you can say that in general, we are now reducing a polynomial of degree n. In general, comma, given n plus 1 distinct tabular points, given n plus 1 distinct points. The points are x0, f0, x1, f1, all the way up to xn, fn. When we have such points, it is possible to find a polynomial of degree at most n. It is possible to find an interpolating polynomial of degree at most n, which passes through the points, So that polynomial is given by, Pn of x is equals to L naught of x f naught plus L1 of x f1 plus so many other terms up to Ln of x fn. And so this you can write as the sum from I is equals to 0 to n Li of x fi. So that's an interpolating polynomial of degree n in general. Now, let me explain what we mean by Li of x in this definition, and also fi. So we said where when we write fi, it means f of xi. That's what we mean. That's the value of f when x is xi, and the Lagrange coefficients Li of x is defined by Li of x is equals to the product. The product is written as this one, a big pi, product from j is equals to 0, of course j not equal to I, all the way up to n, of x minus xj divided by xi minus xj. So when you open up this product, this is what you're going to get. It will be equal to x minus x naught times x minus x1 times x minus x2 times so many of them, and then times x minus xi minus 1 times x minus xi plus 1 all the way up to times x minus xn. Denominator, this is what you'll get. It will now be xi minus x naught, xi minus x1, xi minus x2 so many of them up to xi minus 1, xi minus xi plus 1 times xi minus xn. So look at that kind of an expansion, that kind of a product. If you look at the numerator, we don't have xi. From xi minus 1, we go to xi plus 1. Why do you think we don't have xi? Because there will be xi minus xi, which will be 0, and you cannot be able to divide by 0. So, and in this case, I ranges from 0 all the way up to n. So you can write for I is equals to 0, 1, 2, all the way up to n. So there's so many dots up to n. So this Lagrange coefficient satisfy what we call this kind of a condition, the property. So you can just write, take note that the coefficients Li of x satisfy these conditions, that the sum from I is equals to 0 to n of Li of x, when we add all of them, we need to get 1. And another one is that Li of xj, this should be the same as, it is 1 if I is equals to j, and it is 0 if I not equal to j. This is the same as the Dirac delta function. Dirac delta function written as dij. So the same as the Dirac delta function dij. So let me explain the pattern in obtaining Li of x. So you can just take note that the pattern in computing the Lagrange coefficients in each term is to form the numerator as a product of linear factors of the form x minus xj, and you can see it from here, comma, omitting one xj in each term, the omitted value being used to form the denominator by replacing x in each of the numerator factors. You can see the way we form the denominator. So where there was x, we have replaced by xi, as you can see. So let me explain this using an example. Just a general example on how to find the coefficients. I want us to consider the table with 4 data points. So you can just say, e.g., consider this table. We have x and f of x. I just need 4 data points. So I'll need here x naught, f naught. That should be f naught. Then x1, f1, x2, f2, x3, f3. Those are how many? There are 4 points. So let's consider that table. And now, how do you obtain the Lagrange coefficients? Because here, when you have 4 points, it means your polynomial must be of degree 3. So because of the 4 points, 4 data points, 4 data points means that our polynomial must be of degree 3, P3 of x. It cannot be of degree 4 or even higher. So it is this kind of a polynomial. It is equals to L naught x f naught L1 x f1 L2 of x f2 plus L3 of x f3. So how do you get those Lagrange coefficients? So in this case, L naught of x, when you are at x naught, you bypass that in the numerator. So it will be when you're multiplying, you bypass x naught in the numerator. So we start with x minus x1, x minus x2, x minus x3. This one you divide by, now where there is x in the numerator, you replace that by x naught. So it will be x naught minus x1, x naught minus x2, x naught minus x3. What about L1 of x? When you are at x1, in the numerator, you bypass it. Bypass x1, so we'll start with x minus x naught. I bypass x1, so I will go to x minus x2, then x minus x3. Denominator, now use x1 where there is x, so it will be x1 minus x naught, x1 minus x2, x1 minus x3. The other one is L2 of x. That means to form the numerator, I'll bypass x2. So we'll have x minus x naught, x minus x1, bypass x2, so we'll have x minus x3. Denominator, now use x2 where there is x, x2 minus x naught, x2 minus x1, x2 minus x3. Then the other one is L3 of x. That means to form the numerator, I'll bypass x3. So I'll have x minus x naught, x minus x1, x minus x2. Don't write x3. We don't need it in the numerator. Let's use it in the denominator, x3 minus x naught times x3 minus x1 times x3 minus x2. So that's how to get the Lagrange coefficients when you have a polynomial of degree 3. And you see, the case when n is equals to 1 will take you back to a polynomial of degree 1. And when n is equals to 2, you get a polynomial of degree 2, or simply quadratic interpolating polynomial. For the degree 1 is the same as linear interpolating polynomial. So now, having talked about those Lagrange polynomials, let's now see how to work out the question. So we write work out the question. Our question, we were given the table. Let me take you back to that table. We were given the table of x versus f of x. You are to obtain the polynomial appropriate to approximate the data and also estimate f of 2.5. So let's construct the polynomial for this table. In this table here, we are going to say this is our x naught, this is x1, x2, x3. So this is f naught, f1, f2, f3. So how many points? Data points, there are 1, 2, 3, 4, 4 points. So here we have 4 points, 4 data points. That means our polynomial must be of degree 3, P3 of x, which I've shown you how to get. And so it's the same as L naught of x L naught of x times f naught L1 of x, that should be x, L1 of x times f1 plus L2 of x times f2 plus L3 of x times f3. And for the case of 4 points, I've shown you how to get the Lagrange coefficient. So let's go back and replace the values of x naught all the way up to x3, f naught all the way up to f3, because we have them. So x naught is 1, x1 is 2, x2 is 2, x1 is 1, x2 is 2, x3 is 4. F naught is 3, f1 is 2, f2 is 7, and f3 is 59. So we replace them so that we get the Lagrange coefficients. So I'm not going to write them again because now we have them. For the case of degree 3, I'm not going to write them down again. So let's replace our L naught. In this case, you write L naught of x, that is x minus x1, x1 is 1, x minus, what was our x2? That is 2. Then x minus 4, which is x3. Then over x naught, which is our x naught in this case is 0, minus 1, 0 minus 2, 0 minus 4. Let's work it out. Denominator will be negative 1 times negative 2 times negative 4. That's 8. That's negative 8. So I'll write here negative 1 over 8. That's denominator. Numerator, you just multiply what we have there. It will give you x cubed minus 6x squared plus 8x. X cubed minus 6x squared plus 8x. Do the same to L1 of x. L1, we start with x minus x naught. That is 0, x minus 0. Then the other one, x minus 2, then x minus 4 over 1 minus 0, 1 minus 2, 1 minus 4. Again, this will give you 1 over 3 times x cubed minus 6x squared plus 8x. 6x squared plus 8x. Let's proceed to x2 and lastly x3. Not x2, but L2 of x. This should be able to give us x minus 0, x minus 1, x minus 4 over, now we use x2 in the denominator. X2 is equals to 2, so it's 2 minus 0, 2 minus 1, 2 minus 4. When you work it out, because I know you can simplify, that will give you negative 1 over 4. And that numerator, when you open it up, you get x cubed minus 5x squared plus 4x. X cubed minus 5x squared plus 4x. Then lastly, L3 of x. That is x minus 0, x minus 1, x minus 2 over 4 minus 0, 4 minus 1, 4 minus 2. And so this should give you 1 over 24 into x cubed minus 3x squared plus 2x So if you want to check whether what you have found as the Lagrange coefficients are correct, you need to try adding them. So when I add everything, you need to get 1. If not, then know that there's something wrong somewhere. If I add them, all these ones, the result should give me 1. So when I add, I need to get the answer to be 1. And in this case, it is true, so it means we are correct. Because when you add all those, you get 1. Now, let us now substitute them back into our polynomial. So you say, therefore, our P3 of x is the same as L0 of x F0 plus L1 of x F1 plus L2 of x F2 plus L3 of x F3. So we replace them. The first one, that was negative 1 over 8, negative 1 over 8 times x cubed minus 6x squared plus 8x times our F0 is 3, so times 3 plus the other one is 1 over 3 times x cubed minus 6x squared plus 8x this one should multiply F1, which we got to be 2, then plus negative 1 over 4, remember it's a plus of negative, becomes negative, x cubed minus 5x squared plus 4x. The other f, that is f2, which is 7. And finally, we'll have plus 1 over 24 x cubed minus 3x squared plus 2x times 59. That is the value of f3. So if you simplify, which I know you can do, it is better to leave this in the simplest form. When you simplify this, you need to get x cubed minus 2x plus 3. So therefore, our interpolating polynomial, so you can just say that therefore, our interpolating polynomial P3 of x is the same as x cubed minus 2x plus 3. That is the Lagrange interpolating polynomial for the given data. Of course, it is of degree 3, as you can see. Now we want to use it to approximate f of 2.5. So now estimate f of 2.5. So this is approximately equal to P3 of 2.5, which is equals to 2.5 cubed minus 2 times 2.5 plus 3. And when you press in your calculator, you need to get 13.625. 13.625. So that's the approximate value of f of 2.5 from the given table. I want us to take note that if the explicit form of the collocation polynomial was not required, you see, like here we have expressed it, P3 of x, we know the explicit form. But if we didn't require that explicit form, then we would proceed to estimate P3 of 2.5 directly from the factored forms of the Lagrange coefficients. You see what I mean? That when you are substituting. If we don't ask you to give us P3 of x explicitly, you could even substitute the value of x here. When you are substituting x0, x1, x2, x3, even the value of x you could have substituted here. Instead of x, you will have written here 2.5 so that you just get the value. It will be very easy. So you only do that when we don't need to know the explicit form of the collocation polynomial. So that's all about the univariate Lagrange interpolating polynomial. Remember, it's univariate because it is a function of just one variable x. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving Lagrange interpolation technique. Bye-bye.